Hello, welcome back. This is Calculus by Dr. Oz. So this is the second video in a series. In the first video, we talked about the first learning objective, which was the introduction of the shell method to find the volume of a solid of revolution. So now we have two methods that we have learned so far. One of them is the disk method, and the other one is the shell method. So now we're going to compare these two methods. All right, let's get started. All right, I'm going to try explaining the comparison of the methods with these four pictures. In fact, the first two are the use of washer disk methods based on the type of the axis of revolution, and the last two are more the shell method application. Again, similarly, we have vertical and horizontal axis of revolution. So let's stare at the first one because the first one is about the axis of revolution about y-axis. So it's a vertical axis of revolution. So in the disk method, we always take representative rectangles perpendicular to the axis of revolution. So here we go. This is the reason why we took this type of representative rectangle, and that comes with thickness dy. Okay, since we have a hole here between the axis and the rectangle, so we're going to have a washer. So the volume of the representative washer is determined by inner and outer radii. And as you see that capital R is the outer radii and little r is the inner radii. So we plug in those in the formula so that we get the volume. And here the limits of the integral are determined by c and d values on the y-axis because this integral is going to depend on dy. Okay, and if you want to use the shell method instead of the disk method, and that means you're talking about this picture here, the same region, but again we're using the shell method, so that means we're going to have shells. So in the shell method, we always take rectangles parallel to the axis of revolution. So that's the reason why we take this type of representative rectangle that comes with thickness dx. Okay, and now once you revolve this around, you're going to get a shell, and the volume of the shell is determined by its radius and the height. Here we go, you have h and p, but remember, since we have the thickness dx and the integral is going to depend on x, so p and h are going to be written in terms of x, and for the limits of the integral we're going to use a and b, so these are the x values corresponding to this region. So you see the difference between the disk method and the shell method based on how you set up the integral. So here, as you see, everything depends on dx, and here everything depends on dy. So if the function provided to you, this curve is provided to you as y equals f of x, and go ahead and use the dx type formulation. Okay, if that function is given in terms of y, then go ahead and use dy type formula that's coming out of the washer method or disk method. Okay, so now let's look at the other two. So let's stare at this one and this one because these are both horizontal axis of revolution. In one case we use the disk method, in the other one we use the shell method. So if you use the disk method, again, the way we choose the rectangle is that it got to be perpendicular to the axis of revolution, and here is the representative rectangle. And just immediately to compare this to the last picture here, we use the shell method, so we're going to choose a rectangle parallel to the axis of revolution. So perpendicular versus parallel for disk versus shell method. Okay, so here the thickness is dx, whereas here the thickness is dy. So here all the integral components are written in terms of dx, and in this example everything is written in terms of dy. And what formulas do we need here? Well, the formula that you need here is that you're going to have a washer for this one after you revolve that rectangle or about the horizontal axis. So you need little r and capital R. Okay, and if you just plug them back into the formula, you get this integration. And here capital R and little r must be written in terms of x, and the limits are determined by the x values within the region. So the minimum x is a and the maximum x is b, so the limits would be a and b. Whereas in here, you need p and h, okay, the radius and the height of the shell. So again, these are supposed to be written in terms of y in this case, because the integral depends on y. And the formula goes 2 pi times the radius times height times dy. But this time, since everything depends on dy, you're going to look at the y min and y max values within that region, and these are c and d in this case. Okay, so again, depending on how the function is provided to you for this curve here, you can either use dy type formulation that uses the shell method, or dx type formulation if the function is provided to you in terms of x. All right, let's have an exercise and see what happens if you use one method over the other one. So the example is finding the volume of the solid formed by revolving the region bounded by the graphs y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. And as you can see from the statement of the question, the technique or the method that you're supposed to use is not stated. So that means you're going to decide which technique you want to go with. Okay? But the first thing is first, just go ahead and have your calculator ready and try to come up with this region. Well, first off, you have x squared plus 1. So x squared plus 1 has a graph like this. And then you have y equals 0, which is x-axis. You have x equals 0, which is y-axis. And you have the x equals 1 vertical line. So you're talking about this blue region that's supposed to be revolved around this vertical axis, which is the y-axis. Okay, so as you see in the solution here, let's go with the washer method to start with and see what happens. So to be able to use the washer method, remember, we always take representative rectangles perpendicular to the axis of revolution. And here we go. Our region consists of two subregions. So I have to split the region into two pieces because the representative rectangles would have the lower and upper limits differently. So as you see that here, for example, in this subregion, right, the representative rectangle, the left-hand side of that touches the curve and the right-hand side touches here, whereas for this representative rectangle, the left-hand side is always touching the y-axis and the right-hand side is touching the x equals 1 vertical line. Okay, so since we have two different setups, so we split the region into two subregions. Okay, and remember that if you go with the washer method, as I said, we use the representative rectangles perpendicular to the axis of revolution. So that what that means is, for this case, the thickness is going to be dy. So everything has to be written in terms of dy. When I say everything, remember what we need in the washer method. We need the inner and outer radii. So those are supposed to be written in terms of y. And this curve here is what we said, like y equals x squared plus 1. Y equals x squared plus 1. Okay. And since, again, everything is going to be written in terms of y, you need to have the y representation of, or x equals f of y representation of the curve. So essentially we solve this for x. Okay, so essentially x becomes radical y minus 1. Okay, normally you have plus minus y minus 1, but the minus version is not needed because x's within this region are positive, so we get the positive version of this function. Okay, so then again we need inner and outer radii, but for the second region, this length of, in fact, any rectangle that you pick, not necessarily that representative rectangle, but any rectangle you pick, well, you're going to use only disk method, not the washer method, because the length is always 1, no matter what rectangle you pick. Whereas here, So the inner and you have inner and outer radii, so it's more like a washer technique, okay, that you're going to rely on. All right, so let's look at, well, here, let's just talk about a little bit here. So here, the outer radius obviously is always a 1, right? So this length here is always a 1. So that's why we have r equals 1. And little r is always determined by the curve, and the curve comes with the equation x equals radical y minus 1. So essentially, the way we go is, in fact, let's say like this is y units. This is y units far from this axis. So the corresponding, let's say, x coordinate for that, which is going to give us the little r, is determined by the function that is, in fact, radical y minus 1. Okay? And as I said, the outer radius is just 1. For the second region, outer radius is 1, and inner radius is 0 because we're not really using the washer method, but just the disk method. Okay, so let's go ahead and write down the formulas for each case. So this is the first subregion, and this one is for the second subregion. Y's in the first subregion are ranging from 0 to 1. And in the second region, you have y's ranging from 1 to 2. And outer radius, outer radius, and inner radius. Okay, so you just like write them all and simplify the given uh, integrants, right? So the first one is 1 times dy, and the other one is 2 minus y. And obviously integrate each integral and plug in or substitute the upper and lower limits to come up with the volume 3 pi over 2. So this is a good exercise for you to practice for crunching the numbers essentially. But this is us using the washer method to come up with the volume. So now what I want to do is to use the shell method, okay, shell method, because shell method is going to provide us the volume integral written in one shot. We don't need to split the region into two subregions, okay? And remember that in the shell method, we take a representative rectangle parallel to the axis of revolution. So this is the only rectangle, only type of rectangle you pick. And this is, you don't just split the region because no matter what representative rectangle you pick, the top part of that touches the curve, the bottom part of that touches the x-axis. So they're very uniform. So we're going to write the volume integral in one shot. When you choose a representative rectangle of this sort, so the thickness is going to be dx. So everything written under the integral sign should be a function of x, and we need radius and height. So let's say like this guy here, this rectangle here is x unit far from the axis of revolution. So for that reason, the height is determined by this curve here because the top portion of the rectangle touches the curve. And over there, the curve is written in terms of x anyway in the problem. So y equals x squared plus 1. So this here, height, is going to be x squared plus 1. So we have p, which is the radius, that's x, and also written here, right? And we have the height, here we go, also written there. So then we can go ahead and write down the integral for the x limits ranging from 0 to 1 within the region. Okay, so go ahead and write down the formula, 2 pi times radius times height times dx, and plug in p and h. Simplify. So you have x cubed plus x squared. So this part is in fact 2 pi x cubed plus x dx, integral from 0 to 1. And if you use the power rule for integration, you have x to the fourth plus x squared over 2, and the limits are 0 and 1. And please go ahead and then crunch those numbers to get that the volume is in fact 3 pi over 2, which is the same number obtained by the washer method. Okay, so obviously both methods should spit out the same final number because the volume is the same, right? But the way to get to this number here and here these ways are not the same. One uses the washer method, which required two integrals, right, to be able to represent the volume, whereas in the shell method, we wrote the volume integral in just one shot. All right, it's practice time, so go ahead and visit the recitation PowerPoint, and you will see that the fourth exercise is looking like this. So we have a plane region bounded by two curves, y equals 1 over 3x cubed and 6x minus x squared. And we're going to revolve this region about the line x equals 3. X equals 3 is a vertical line, so it's not y-axis, but just x equals 3 as a line. So you're going to revolve the region about that line. And in the question statement, as you see that, use either disk or shell method. In fact, you can try using both of them just to see what's going on. But the point is that you want to get to the final result in a very short way, in an optimal way. So you will see if the disk or shell method provides you the shortcut. Okay, so that's something that you're gonna sort of like see within the video. You can go ahead and start working on it by yourself. But at the end of the day, you will see that one technique is more powerful than the other technique. And within the video, you will see how I assess which technique or which method I use for the rest of the video. Please check that out. And the region looks like this for your own reference. And as you see that, since the axis of revolution is this line here, and since the functions are provided to you in terms of x, the picture gives you the hint of what technique you're going to use. So check that video out. Okay, but after the revolution, this is kind of like picture or three-dimensional object you get at the end of the day. Okay. And the second exercise in the list, again, you're given a region bounded by two curves, radical x and x squared. In one case, you're going to revolve the region about x-axis. In the other case, about y-axis. So this question is not asking you to evaluate the integrals, but just writing down the integrals coming out of the technique you decide, you assess to use, disk or shell method, and you're gonna sort of like assess that by yourself. And please check the video out as well to see what I'm gonna have to do to pick what technique is the one providing you the shortcut. And the final exercise in the list is sort of like an inverse problem. So you're given an integral that represents the volume of a solid of revolution. So this integral is written in terms of either like washer method or shell method. So you're going to decide which, and then once you decide which one, then you're going to try to determine the plane region that's revolved. And you're going to also determine the axis of revolution. Please watch the video to see how I attack this inverse problem by using the methods that we have learned so far. All right, this was the last exercise. Please go ahead and watch all of those videos, and then you can start the homework assignment for this section. All right, so this is the end of the video. Thanks for watching. I'll see you in another video. Bye.